Is the sound still coming? Okay, let's start with this problem. A sequence of 3 real numbers forms an arithmetic progression with the first term, 9. So we have an arithmetic progression. So let's say the first term is 9, the second term is 9 plus d, and the third term is 9 plus 2d. Okay, so sorry about that. There were some issues with the humming sound. I'm now trying these headphones and see if they'll work to help eliminate the sound. And as you can see here, I wrote a hint, which basically says to use the arithmetic sequence and add the values to form a geometric sequence. So as I wrote earlier, we have 9 plus 9 plus 9, comma 9 plus d, comma 9 plus 2d. And then we add 2 to the second term to get 11 plus d, and add 20 to the third term and to get 20 plus 2d. 29 plus 2d, sorry. And now we know that these three values form an arithmetic sequence. Okay, so what we can do to solve this is we can see that the common ratio between terms has to be the same. So what that means is that 11 plus d over 9 will have to equal to the common ratio, r, and that will also be 29 plus 2d divided by 11 plus d. Now we can just cross multiply. So we cross multiply, we get d squared plus 22d plus 121 equal to 18d plus 261. And then from here we can get that d squared plus 4d minus 140 is equal to 0. And now what we can do is we can factor this quadratic. So we can factor this quadratic by seeing that the sum of the two values must be, and then we can just get d plus 14 times d minus 10 equal to 0. And that means d is either negative 14 or 10. And this is something that you could do and actually get it wrong by doing this, is you would just say that, okay, negative 14 or 10. Oh, let's take the positive one, 10, and then we say that, okay, the third term is just going to be 29 plus 2 times 10, or 49. And you might think this is the answer, but that's not true. The reason is we want the smallest possible value for the third term in the geometric progression. So since we want the smallest possible value for the third term in the geometric progression, we actually have to take the smaller value of d, which is negative 14. So to take the smallest value of d, we get that 29 plus 2d equal to 29 plus 2 times negative 14, which is equal to 29 minus 28. But that's just 1. So 1 is our answer, our real answer here. So now let's start off. Now let's continue on with our problems in number theory. So we're going to explore some more basic number theory problems first, and slowly progress into some newer techniques that we can use to solve number theory problems. Let's start off with this problem. What is the smallest positive integer that is neither prime nor square and has no prime factor less than 50? So if it has no prime factor less than 50, its prime factors must consist of numbers more than 50. So the prime numbers that are more than 50 are 53, 59, etc. These are the prime numbers more than 50. And we want a number that's not prime. So we don't want a prime number, so we cannot just have 53, because that's prime. We want to have the product of two prime numbers, or three prime numbers, or the product of some amount of prime numbers. So then what we can try is maybe 53 times 53. But then you notice that 53 times 53 is a square number, so this also doesn't work. So the smallest possible value is just 53 times 59. The reason it's 53 times 59 is these are the two smallest prime numbers, and a quick way to multiply this is to realize that this is just 56 squared minus 9, which is just 3127. 56 squared is 3136, minus 9 is, so you get 3127. And I got this, the reason how I got this is because 53 times 59 is 56 minus 3 times 56 plus 3. And this is a nice mental math trick, and this is just going to be 56 squared minus 3 squared. So that's a useful mental math trick that can be very helpful, so it's very, very good to consider knowing. And this is just 3127. So that's how I found that 3127 is our answer. So are there any questions? Okay, now let's move on to the next problem. Each of the digits 0 through 9 is used only once to make two 5-digit numbers so that they have the largest sum possible. Which of the following could be one of the numbers? Okay, so we have 5 numbers plus another 5 numbers, right? And we add these numbers together, and then we're given that 2 so they have the largest possible sum. So how can we do this problem? Well, first notice that we have the numbers from 0 to 9, right? So since we have the numbers from 0 to 9, we want to maximize the total sum. We want to put the larger numbers in the largest place value. Because when the larger numbers in the largest place value, they're going to have a larger effect on the overall sum. So the largest two numbers are 8 and 9. So we put the 8 and the 9 in the highest place value. But do remember that we can also flip these values. So we can put 9 and 8, or we can also put 8 and 9. The sum is anyways going to be the same because we have 8 and 9 in that place value. The next numbers are 7 and 6. So we can put 7 and 6 in this place value, and then we can flip them around. And they're the same thing essentially, because we want to put the highest ones in the highest places, and the other higher ones we can still put them, but we don't want to put them in the highest place value. You can put them in the second place value, because the highest place value have the greatest impact on the final number. So we want to maximize that. The next one is the third place value, which is going to be 5 and 4, and we can again flip them. The next one will be 3 and 2. And the final one will be 1 and 0, because it's not really making a big impact when it's just in the units place. So essentially, the numbers will have to be of the form. They have to be 9, 8 in the first digit, 7, 6 in the second, 5, 4 in the third, 3, 2 in the fourth, and 1, 0 in the fifth. So now we just check which of these choices satisfies these conditions. And we can find that this choice is the only choice that works because we have 8 in the first place, 7 in the second place, 4 in the third place, 3 in the fourth place, and 1 in the fifth place. So that's our answer for this problem. Let's now move on to the next problem. For any positive integer m factorial denotes the positive product of the numbers from 1 through m. And we covered this in the combinatorics class, if you remember. But now we're going to use this in a number theory context. What is the largest integer n for which 5 to the n is a factor of the sum 98 factorial plus 99 factorial plus 100 factorial? Well, that's a lot. That seems like a lot, right? So we can actually simplify our expression. So what we can do is we can take 98 factorial common amongst the whole expression. So then we have 98 factorial is just 1 times 98 factorial. 99 factorial is just 99 times 98 factorial. And 100 factorial is 100 times 99 times 98 factorial. So we can now factor it in this expression. And now this is just equal to 98 factorial times 1 plus 99 plus 9900, which is 100 plus 9900, or 10,000. Okay, so now we're going to count how many powers of 5 are in each of these terms. We can see that there are 4 powers of 5 in this second term here. But this first term is a little bit more tricky. So how many powers of 5 are there going to be in this first term? Well, we can actually use a really clever trick. So 98 factorial is equal to 1 times 2 times 3 times 4 times 5, dot, 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 all the way till times 98. So how many of these numbers are multiples of 5? There are 98 divided by 5 equal to 19 multiples of 5 less than 98. How many numbers less than 98 are multiples of 25? Well, first of all, I should actually make it more clear here. We have the numbers from 1 to 98, and how will we get powers of 5? So when we multiply these out, when will we have a power of 5? We will have a power of 5 when we're multiplying a number that's a multiple of 5. And we have 19 of these such numbers. But some numbers have more than one power of 5. some numbers that are multiples of 25, like 75 for example, has 2 powers of 5. So now we have to add the number of powers of 5, the number of these multiples of 25, because they're adding additional powers of 5. So then we add 98 divided by 25, because the numbers that are multiples of 25 have 2 powers, an additional power of 5, to get 3. And now we can see that there are a total of 22 factors of 5 in 98 factorial. So this is just 5 to the 22 times 5 to the 4, which is 5 to the 26. So the largest power, the largest n, is just going to be 26. And this concept right here of finding the number of factors of factorial is really common, especially in math counts. So it's a really good trick to know. So in general, if you have a number n factorial, so this is separate from the problem. So n factorial, let's say you want to find how many factors of a number are there in n factorial. You would just count the number of multiples of, let's say, we want to find how many factors of k are there. So how, or better phrase, basically what power of k is the maximum that divides n factorial. So a nice trick to doing these types of problems is to see how many of those n numbers that we multiply are multiples of k, how many are multiples of k squared, how many multiples of k cubed, so on, and you add them all together, because that gives you the total number of powers of k. So that's a nice trick that you should know, especially if you're doing math counts. Okay, so now let's move on to these next problem. Laura added 2 3-digit positive integers. All 6 digits in these numbers are different. Laura sums the 3-digit number s. What is the smallest possible value for the sum of the digits of s? Sum of the digits. Okay, this is a little bit different from the previous AMC 8 problem where we have to find maximize the sum. It's a variation of it. So let's see what we can actually do. So we have a 3-digit number plus another 3-digit number, and we're adding them together to get another 3-digit number, we're told. Okay, so how can we actually minimize the sum of the digits? How can we minimize the sum of the digits? So a hint here is to realize that the sum of the digits is maximized when you have the largest possible numbers, but not exactly. So let's say you do 7 plus 3, right? We're adding 2 really small numbers, you get 10. Because we carry one of the numbers, we carry the 1. But that's only a sum of 1. This only has a total sum of digits of 1. But as you can see here, the original 2 sum of digits was 7 and 3. So now we made the sum of digits so tiny. The reason the sum of digits became so tiny was because we carried over. Because now we got a 0 here, which took away all those extra digits. If we had added 7 and 2, for example, we would have got 9. 9 has a pretty high sum of digits, which is 9. So it's just much higher. So the idea here is to say that when we carry over a 1, we're going to just leave a 0 behind. Then we're left with a really small sum of digits. So let's see if we can apply this to our problem here. So let's say we put 7 and 3 in these 2 digits. Now we get a 0, which is good. Because we want to make the sum of digits as small as possible. So we want to add zeros so that the zeros will be there and the other digits won't really affect it at all. So we put a 0 here and we carry a 1. Okay, so now what? Well, we see that these 2 digits, we want them to sum to 9. Because now we already have a 1 carry, so we want 2 numbers that will sum to 9. Because then we have 9 plus 1, which will be 10. And then from a 10, we just carry a 1. So it's best to put 5 and 4 here. And make sure to remember that all the digits in the numbers are different. So for example, we could not put 6 and 3, for example. So 6 and 3, this wouldn't work. Because now we have 2 3s. So that's why we put 5 and 4. And then again, we have a 0, and we carry a 1. But now, again, this time we can't carry. Because our sum has to be a 3-digit number. The sum has to be a 3-digit number. So if we make a carry, then it will become a 4-digit number. So now at this point, we just want to minimize this digit. Make it as small as possible. So we just choose our 2 smallest numbers, which are just going to be 1 and 2. And the reason we can't choose 0 is 0 can't be at the start of a 3-digit number, because then it won't be a 3-digit number anymore. So now the minimum possible sum here is 1 plus 2 plus 1, which is 400. So as you can see, this is a sum of digits of only 4, which is pretty small, and is our answer for this problem. Okay, so now let's take a look at the next problem. We're now going to take a look at money problems. Loki, Mo, Nick, and Ott are good friends, but Ott has no money. But the others did. Mo gave Ott 1/5 of his money. Loki gave Ott 1/4 of his money, and Nick gave Ott only 1/3 of his money. But it turns out they all gave Ott the same amount of money. So what fractional part of the group does Ott now have? So an easy way to go about this is to set up a system of equations, a really basic one. So you have Ott, you have Loki, I'll just say L, O, we have Nick, and we have Mo. And we're given that they all give the same amount of money to Ott. So how about we just say they all give X dollars to Ott? So let's just say X dollars. X. So they all give X dollars to Ott. But we're given that Mo gave Ott 1/5 of his money. So what does that mean? If Mo give X dollars, and that X dollars is 1/5 of his money, he must originally have had 5X dollars. Same thing for Nick. If Nick gave Ott 1/3 of his money, he must have originally had 3X dollars. And Loki must originally have had 4X dollars to give 1/4 of his money to Ott. But now they don't have 5X, 4X, and 3X dollars anymore. Mo only has 4X dollars now because he gave one to Ott. Nick only has 2X dollars now because he gave one to Ott. And Loki only has 3X dollars. And now Ott has 3X dollars because he got 3X from each of the 3 people. So now Ott has 3X over 3X plus 3 over 3X plus 3X plus 4X plus 2X. And this is just 3X over 12X or 1/4. So Ott has 1/4 of the group's money now. Okay. So now let's take a look at this problem. You have 9 coins, a collection of pennies, nickels, dimes, and quarters having a total value of $1.02, with at least 1 coin of each type. At least 1 coin of each type. This is a very important condition, and it's happened many times to many people, including me, that we forget to include this condition at the end. So make sure to always pay attention to the wording of the problem. Sometimes it'll say at least 1, or else, otherwise make sure to be careful about these kinds of things. And we have to find how many dimes you must have. So firstly, if you must have $1.02, then you must have at least 1 penny, 1 nickel, 1 dime, and 1 quarter. So let's just subtract off the 1 nickel, 1 penny, 1 dime, and 1 quarter. So we subtract off, let's just say we have 102 cents. So we have to get 102 cents total. We must have 1 penny, 1 nickel, at least 1 nickel, at least 1 dime, and at least 1 quarter. And then after that, we have 61 cents left. Okay, so now we have 61 cents left, and we want to give it to the different coin types. So we have 61 cents, and we want to somehow get 61 cents somehow. But wait, remember that we already used 4 coins. We already used 4 coins, right? These are 4 coins already used. So now we have to make 61 with 5 coins. So now for this problem, it just requires a little bit of casework. If we have 0 quarters, it's impossible to get 61 cents, because if you have 0 quarters, even if all the other 5 coins are dimes, that would only be 50 cents. So 0 quarters is too little. If we had 1 quarter, now that this means we would have to have 36. This means we would have to have 36 cents for 4 coins. And is this possible? Well, we can see that one of those coins has to be a penny. Since we have 36 cents, there's no other way to get that 1 cent coins. And then we're left with 35 cents to make with 3 coins. And that's not possible again. Because even if all the coins are dimes, it would not reach that 35 cent limit. So this case also doesn't work. The next case is 2 quarters. If we use 2 quarters, now we already have 50 cents gone. So now we have 3 coins. We want to make 50 cents are gone. We have to make 11 cents with 3 coins. And again, one of those cents has to be a penny. So then we're left with 10 cents for 2 coins. And we can very easily do this by just having 2 nickels. So now we can see that we can have 2 quarters along with 2 nickels, and now we get the 61-cent limit. And again, another common mistake that people would think is, okay, so we have 2 quarters, 2 nickels, so we have no dimes. The answer is 0. But that's not true, again, because remember, even though we subtracted it off in the beginning, we still have to include that coin in our total count. We still had 1 penny, at least 1 penny, I'm sorry, it has to be 1 penny here too. We already had at least 1 penny, 1 nickel, 1 dime, and 1 quarter, so why don't we just add that on? So we can just add that on. We got that we have 3, now we have 3 quarters, 3 nickels, and 1 dime, and 2 quarters. Sorry, 1 additional quarter, so we already added that down. And then 2 pennies. And from here, we see that we have 1 dime, so 1 is our answer. Let's move on to the next problem. If the average of all the pennies, nickels, dimes, and quarters in Paula's purse is 20 cents, if she had 1 more quarter, the average would be 21 cents, so 1 more quarter. How many dimes does she have in the purse? So dimes. So how can we do this? Well, the average of some number of coins is 20 cents. So let's just say that Paula has n coins. So if Paula has n coins, if you didn't see it here, also, sorry, but if it was off the page, if you didn't see it. So here, see, basically what I did is I did the different cases, and you add that on, one penny, 1 nickel, 1 dime, 1 quarter, and then we get that there's 1 dime. Is 20 cents. So we have, again, resuming, we have 20 cents and coins with a value of 20 cents. And then we have 1 more quarter. And now the average is 21 cents. And that's the average of n plus 1 coins. So n plus 1 coins now have an average of 21 cents. So now we have 21 cents for the average of n plus 1 coins. So now what we can do is we can just cross multiply to both sides. We'll just get 20n plus 25 equal to 21n plus 21. That means n is just going to be equal to 4. So that means that we have 4 coins that had an average of 20 cents for a total of 80 cents. So 4 coins had a total of 80 cents. So now, how can we find out a case? We can do something very similar that we did in the previous problem. We'll just do a little bit of casework on how many quarters we have. Again, 0 quarters is impossible. Same thing for 1 quarter, because 1 quarter would still leave 55 cents for 3 coins. And in fact, even 2 quarters is not possible, because 2 coins would still leave 30 cents for just 2 coins, which is not possible given that our next maximum is a dime, and a dime is only 10 cents. So even 2 quarters is not possible, but 3 quarters does work. If we have 3 quarters, that means that out of these 80 cents, we already got 75 cents. And we just need 5 more cents in order to complete our 80 cents with 1 coin. So we need an additional 5 cents in 1 coin, and we can do that by adding a nickel. So that means in the purse, originally there was 3 quarters and 1 nickel. But now, after adding, now there's 1 more quarter. So now there's going to be 4 quarters and 1 nickel. So how many dimes are there? 0. Let's take a look at the next problem. Joe is a collection of 23 coins consisting of 5-cent coins. And as you can see here, these kind of coin cent problems, try to do some casework on the number of quarters, dimes, nickels, they come pretty often, so it's worth knowing how to solve these problems in general. And 25-cent coins. He has 3 more 10-cent coins than 5-cent coins. The total value of his collection is 320 cents. So 23 coins. So he has, let's just say he has X 5-cent coins, so 5-cent coins. Then X plus 3, because he has 3 more 5-cent, 10-cent coins than 5-cent coins, 10-cent coins. So, and then he also has some nickels, some quarters, some 25-cent coins. And they're given that these sum to 320. So they're given that each of these X coins have 5 cents, so 5 times X, so 5X plus 10 times X plus 3, because each of those X plus 3 coins has a value of 10 cents, plus 25Y is equal to 320. And we can expand on both sides. We get 5X plus 10X plus 15 plus 25Y, which means that there's 15X plus 15 plus 25Y equals to 320, which means 15X plus 25Y is 305, which means 3X plus 5Y is just going to be equal to 61. So I'll just mark this equation. And now we don't know really what to do, but the only thing we really haven't used is 23 coins. So another really good problem-solving strategy is to, whenever you're stuck, look at the information you haven't used yet. So in this case, we have not used the fact that he has 23 coins. So what does that mean in terms of equations? Well, that just means that we have x plus 3 plus y equal to 23. And that means that 2x plus 3 plus y is 23, or 2x plus y is 20. Okay, so now what can we try to do from here? So now we have these two equations in terms of the number of coins of each kind. So is there any way we can try and maybe solve this equation now? Okay, so what we can do here is we can see that so now what we can try doing is that we have sorry, I think I said something here. It should be plus 30, not 15. So now this becomes 290 actually, which means it's going to be 58. And now what we can do is we can just use the diagonal product method for solving this equation. And if you don't remember, you can always check out the video I have on how to use this. So we can just do 1 times 58 minus 5 times 20, which is negative 42, divided by 1 times 3 minus 2 times 5, which is negative 7. This gives us 6, which is the value of x. And then from here, we can see that the value of y is just 8. Move that up. So now we know that the value of x is 6, the value of y is 8. So that means he has 6 5-cent coins and 8 25-cent coins. So he has 2 more 25-cent coins and 6-cent coins. So that is our answer for this problem. Let's now take a look at the next problem. The GCD of two numbers is 12, and the LCM of the same two numbers is 240. Find the product of the two numbers. So we're actually going to explore a really nice trick here for this problem. So what you can see is that, let's say we have these two numbers. So this is something that's going to be, I'm just discovering, talking about a trick right now. Right now it's unrelated to the problem, what we're doing. So let's just say we want to find, we have the numbers 3 to the 0. And then the LCM is just going to be the larger exponent of the prime factor. So 2 to the 3, 3 is larger, and 1 is larger. So 2 to the 3 times 3 to the 1. So a really trick that we can use here is that the product of the GCD and the LCM is equal to the product of the two numbers. Here's the reason why. When we're multiplying the GCD and LCM, we multiply both prime factors of 2, because we multiply the larger prime factor in the LCM and the smaller prime factor in the GCD. And then same thing for the power of 3. But when we're just multiplying the two numbers plainly, when we just multiply them just plainly out together, we see that when we multiply them out together, we just multiply both prime factors of 3, both prime powers of 2, and both powers of 3. So it's essentially the same thing as just multiplying them out directly when we do the GCD and LCM. So that's a really trick to hear. You can just verify this. This is 2. This is 24. When you multiply them, you get 48. When you multiply 8 and 6, you also get 48. And this is a really clever trick application here. So this is a really clever application of this trick here. So whenever we multiply two numbers together, it's the same as just multiplying their GCD and LCM. It's the same product. Because we're multiplying the larger power of 2 and the smaller power of 2, the larger power of 3, smaller power in 3. So we're essentially just multiplying the two numbers. So in this problem here, since the GCD of two numbers is 12 and the LCM of two numbers is 240, the product of their two numbers is just going to be 12 times 240, which is 2880. Okay, and for most people who don't know this trick, what they would do is they would just go on hunting and try to figure out values such that the GCD is 12 and the LCM is 240. They just keep trying values until they got some values that maybe worked, and that would take a lot of time. That's how most people who don't know this trick would approach this problem. But now that you do know this trick, you can very easily do this very quickly by just multiplying the two numbers. And this can be a very handy trick. So now let's look at the next problem. If the least common multiple of two numbers of A and B is 12, and the LCM of B and C is 15, we want to find the LCM of A and C. Okay, so what we can see here is that the LCM of A and B, the LCM of B and C, divide 12 and 15. So the idea here is that LCM of A, B is going to be a factor of the LCM of A and B, because the LCM of A and B has factors from both 2 and 3. So B will just divide LCM of A and B, or B will be a factor of the LCM of A and B. So B will be a factor of this quantity. Similarly, B will also be a factor of the LCM of B and C. Since the LCM of B and C is just going to take the factors of B and C together. So B will be a factor of both the LCM of A and B and the LCM of B and C. So if B is a factor of the LCM of A and B and the LCM of B and C, B is also a factor of 12 and 15. So B is going to be a factor of 12 and 15. And that means that B will be a factor of the GCD of 12 and 15, which is equal to 3. So now we know that B is a factor of 3, because it was a factor of the LCM of A and B and the LCM of B and C. So what are the different possible values of B? Well, we can either have B equal to 1 or B equal to 3. If B is 1, then A will have to be 12, exactly. Because it has to have all those factors that are in 12, and it cannot have any more factors. And then C will have to be exactly 15. So then C would have to be 15. But if B is 3, and in this case, our answer would just be equal to the LCM of 12 and 15, which is just going to be equal to 60. And this could be the answer, but what about B equal to 3? If B is 3, so if B is 3, then A, we want to minimize. We want to find the least possible value of the least common multiple of A and C. So we don't want to give too many factors to A and C. So at minimum, A will have to be 4. Because then 4 times 3, you have to get all the factors so that it will have 12. And similarly, C will have to be 5. So that they have a factor of both 3 and 5 in B and C. And then we see the LCM of 4 and 5, or B and C, or A and C, is just going to be equal to 20, which is clearly much smaller than 60. So our final answer is just going to be 20. And as you can see here, we just looked at the fact that B had to be a factor of the LCM of A and B, and the factor of the LCM of B and C, to find that we can just find the values of B and find that the LCM of 4 and 5 is 20. So now let's take a look at this next problem. Each piece of candy in a store costs a whole number of cents. Casper has enough money to buy 12 pieces of red candy, 14 pieces of green candy, 15 pieces of blue candy, or n pieces of purple candy. A purple candy costs 20 cents. What is the smallest possible value of n? So yeah, let's say that the money, M, is equal to 12 times the cost of red candy, or is equal to 14 times the cost of a green candy, or is equal to 15 times the cost of a blue candy, or is equal to n times the cost of a purple candy, which is 20 cents. Note here that now we have n pieces of purple candy that cost 20 cents, rather than having the number of pieces of the blue candy, which we don't know how many blue candies we bought. So now what we know here is that m will have to be a multiple of 12, 14, 15, and 20, right? Because m is equal to some numbers times some variables. So that means that m will have to be at least the LCM of 12, 14, 15, and 20. So what we can see here is that this is just going to be equal to, we have two factors of 2, 2 squared. We have a factor of 3, a factor of 5, and a factor of 7, which is 420. So m will have to be at least 420, because it has to be a multiple of all these different constants here. So m will have to be at least 420, and it can be more, it can be multiples of 420, but we want the smallest possible value. And the reason we want to minimize the value of n, and m is just going to be an n times 20. So if you want to minimize the value of n, we want to minimize the value of m. So the minimum value of m is just 420. And from here we can see 420 is n times 20, which means n is 21. Is our answer? Okay, so now let's move on to our break for today. Thanks to our sponsor. We're going to be raffling prizes again. So we're going to be raffling a daily challenge course by Potion Low, which has a $149 value, one art and problem solving $25 gift certificate, and 2 Wolfram notebook subscriptions. So you can fill out the raffle form. It will be posted in the chat. We're going to take around a 5-minute break. You can also try another problem I will show in the meantime. You can also try this problem in the meantime. Okay, so let's get started on this problem. For how many values of k is 12 to the 12 the least common multiples of 6 to the 6, 8 to the 8, and k? So 6 to the 6 is equal to 2 to the 6 times 3 to the 6. 8 to the 8 is equal to 2 to the 3 to the 8, which is 2 to the 24. And we're asked to find for what values of k is the least common multiple of these three numbers and k going to be equal to 12 to the 12. So let's just say k is 2 to the a times 3 to the b. So what is 12 to the 12? The LCM of these three numbers. 12 to the 12 is equal to 4 to the 12 times 3 to the 12, which is 2 squared to the 12 times 3 to the 12, which is 2 to the 24 times 3 to the 12. So we want the least common multiple to be this quantity. So as you can see here, we already have a factor. We've already got 2 to the 24 term here. Well, we only have 3 to the 6 term, and we need a number that has a factor of 3 to the 12. So that when we take the LCM, it's going to be 3 to the 12. So that means k must have b to be exactly 12. The reason is that we must have a factor of 12. Like I said earlier, the LCM of the numbers must be the largest exponent of all the primes of 3. Therefore, at least one of them must be 12. And since the 6 to the 6 and 8 to the 8 don't have a power of 3 for power of 12 for 3, this k must have 1. Now what about the exponent of 2? Well, a can really be anything from 0 to 24. Sorry, I should say 0 to 24. The reason they can be anything from 0 to 24 is that it doesn't really matter what a is, as long as it's not more than 24. Because if it's more than 24, maybe like 25, for example, then the LCM now has become 2 to the 25, rather than just 2 to the 24. So it can be anything from 0 to 24. And how many numbers are there? They're just going to be 24 minus 0 plus 1 goes to 25 possible numbers. So 25 is our answer. Okay, so now let's move on to the next type of problem, which is test scores, which is again another very common topic on these types of contests. Sorry about that. Isabella must take 4 100-point tests in her math class, and her goal is to achieve an average grade of 95 points. If her first two scores are 97 and 91, after seeing her score on the third test, she realizes that she can still reach her goal of an average of 95. What is the lowest possible score she could have made on the third test? So in order to get an average grade of 95 on the fourth test, Isabella must have had 95 times 4 equals to a total sum of 380 points. Because again, 95 average, there's 4 of the scores. Because 380 is the total sum of all 4 tests. And the first scores were 97 and 91. So we just subtract the sum of 97 and 91, or 188, off. Subtract that off, we get 192. So now we know that the remaining 2 test scores, x plus y, must sum to 192 as well. So if the remaining 2 test scores must sum to 192, what's the lowest possible value of x? Well, the lowest possible value of x will exist when y is as high as possible. So y can be at most 100. So if y is at most 100, if y is at most 100, x can be at the very minimum 92. Because if x is any less than 92, 91 for say, then now the total sum is only 191 at most. So then you can't achieve her average of 95. So minimum, she could have gotten 92 on the first test. 92 is her answer. So now take a look at the next problem. Lalia took 5 math tests with a maximum of 100 points. So again, we're in these types of 100-point test problems. Lalia scores on each test is an integer between 0 and 100 inclusive. Lalia received the same scores on the first 4 tests, and then received a higher score on the last test. Her average score on the 5 tests was 82. How many possible values for the Lalia score on the final test? So 5 tests each have an average of 82. So the total sum is 410. And as you can see here, we're using a very similar process that we used in the previous problem. So the total score has to be 410, but now we have, let's say the first 4 tests all had a score of x, and the last test had a score of y. What this means is that 4x plus y must be 410. So now what can we really do here? We have to look at the different possibilities. Okay, so we can see here that 4x is a multiple of 4, right? But 410 leaves a remainder of 2 when divided by 4. So if 410 leaves a remainder of 2 when divided by 4, and 4x is a multiple of 4, y must also leave a remainder of 2 when divided by 4. Because then when we add a number that leaves a remainder of 2 when divided by 4, and a number that is a multiple of 4, you get another number that leaves a remainder of 2 when divided by 4. So that means y must leave a remainder of 2 when divided by 4. So now, what are the different possibilities? So what you can notice here is that, again, y has to be 2 more than a multiple of 4. It has to be between 0 and 100. So we're given that y has to be the highest score on the test. So that means y has to be greater than 82, or at least 83. So y has to be in the range from 83 to 100. Y has to be from 82 to 100 points. And we know that y has to be 2 more than a multiple of 4, or it has to leave a remainder of 2 when divided by 4. So then the different possibilities for y are 86, 90, 92, and 96. 92, 94, and 98. And so there, 4 is our answer. Let's now move on to the next problem. Mr. Patrick teaches math to 15 students. He was grading tests and found that when graded everyone's tests except Peyton's, the average grade was 80. After he graded Peyton's test, the average became 81. What was Peyton's score on the test? Okay, so he teaches math to 15 students. In his grading test, he found that when he graded everyone's except Peyton's, the average was 80. Then now the class is 81. So there's 2 ways of solving this problem. The first one, the standard one, probably more straightforward way of doing this, is just to write a system of equations. So 15 students. So before, there were just 14 students who have a score of 80. So 14 students who have an average score of 80, plus Peyton's student, Peyton's score, P. And then the new average, when you divide it by 15, is 81. That means that 14 times 80 is going to just be equal to 112, 0. So 14 times 80 is 1120, plus P equal to 15 times 81, which is just going to be equal to, well, it's 1215, which means that P equal to 95. So Peyton's score is 95. So this is method 1. Now let's look at method 2. So method 2 is actually a lot simpler. So let's say we have 14 students, 14 of them. They have an average score of 80. So they all have an average score that's 1 less than the average. So let's just say they all have an average of -1. And the reason I'm saying -1 here is the average is 81, and they all have scores of 80. So right now I'm looking at the relative number to the average. So right now they all have a relative -1 to the average. They're all 1 less than the average. So I'm just saying -1. So now, what must Peyton's number be in order to cancel out all these -1s? Peyton's number must be 14. because these all sum to negative 14. So in order to cancel it out, we must have Peyton's score be 14. So this must be 14. So if Peyton's score is Peyton's score has to be 14 more than the average. So if the average is 81, Peyton's score has to be 81 plus 14, which is 95. So Peyton's score is 95 here. And then the reason that this trick works is that if you can imagine all the numbers relative to all the averages, if you look at all the numbers relative to all the averages, these are all relatively one less than all the averages. So in order to cancel it all out, this last number must be a little bit more. They all have to be a little bit, they have to also cancel out all those negative ones relative to the average. So this has to be 14 more than the average. So negative 1 basically means it's 1 less than the average, 1 less than the average. And this has to be 14 more than the average, so it has to be 95. Okay, so, oh yeah, the reason, some of you are asking this in the chat, the reason you guys are saying, oh, how can you just assume all the scores are 81? So what I'm doing is I'm assuming that since the average is all 81, the average of all 14 students beforehand is 80, we'll just assume that all those scores were 80, because if all those scores are 80 beforehand, then 81, they're relative to the average, they have 81, or maybe, how about I explain an easier way, so hopefully this will be more clear. So all the 80 students, they have an average of 80. So overall they have 14 students who have negative 14 less than the average. Because those 14 students are 1 less than the average. And then after that, we just add 14 to 81 to get 95. So on average, it's going to be 1 less. Maybe this will be 3. This does not necessarily all have to be negative 1. But on average, it's going to be 1 less than the average. So in total, it's going to be negative 14, or 14 less than the average. So we must have 95. Let's now take a look at some miscellaneous number theory problems. So what's the largest power of 2 that divides 13 to the 4 minus 11 to the 4? So 13 to the 4 minus 11 to the 4. Do you notice anything about this expression? Anything that we know about factoring, or do you notice anything about what we can do with this expression? So what do you really notice about this expression? Okay, so something that's a really, really clever trick in this expression is that 13 to the 4 is 13 squared squared. And 11 to the 4 is 11 squared squared. And you might be asking, why am I doing this? The reason is, we're going to actually do something really, really clever here. If A is 13 squared, and B is 11 squared, we can just say, this is A squared minus B squared. We know that A squared minus B squared is just A minus B times A plus B. So now we just factorize our expression. And now what we can do is so we can apply times 13 plus 11 times 13 squared plus 11 squared, which is 2 times 24. Two times 24 times 290. And what is the largest power of 2 that divides this? The largest power of 2 that divides this is just going to be, well, largest power of 2 that divides 2 is just 1. Largest power of 2 that divides 24 is 8. Or I should probably just write 2. I should be more clear. The largest power of 2 that divides 2 is just 2 times 8 times 2. Because we can only divide by 2. The maximum power of 2 that divides it is just 2, 8, and 2. We multiply them together to get 32. It's the largest power of 2 that divides the multiplicate of these expressions. And I'm sure all of you might be thinking that, oh, you could just technically evaluate these together. You could just evaluate them, and then from there you could find out that you could evaluate these super large expressions, you multiply them out, and then you could just divide them. Yes, that would work, but that would take a lot of time on the AMC. That's a very time-taking way of doing this problem. And by using the difference of squares, now it was a pretty quick problem. All we have to do is use difference of squares, and then look at the factors in each of the three products of the number. Okay, so students guessed that Norm's age is 24, 28, 30, 32, all the way till 36, 38, 41, 47. So let me just write that out. It's 24, 28, 30, 32, 36, 38, 41, 44, 47, 49. And if you count these, you see that there are a total of 10 guesses. And he says the first condition is that at least half of you guessed too low. So if there are 10 people, that means at least half of the people. So at least 5 people guessed too low. At least 5 people should be up till here. So if at least 5 people guess too low, that means we know his number, Noah's number, has to be greater than 36 or at least 37. So greater than or equal to 37. His number has to be greater than or equal to 37. Somebody's asking, explain 2 times 8 times. So should I explain the 2 times 8 times 2 again? So the idea here is that the maximum power of 2 that divides 2 is just 2. The maximum power of 2 that divides 24 is just 8. The maximum power of 2 that divides 290 is just 2. So easier said, let me just explain. 2 times 24 times 290. So what power of 2 divides 2? Well, that's just going to be 2. Because 2 is the largest power of 2 that divides 2. And 8 is the largest power of 2 that divides 24. And 2 is the largest power of 2 that divides 290. So that's why we have 2 times 8 times 2. Because now we take the largest powers of 2 from these expressions and we multiply them together. So basically we have 2 times 24, 290. The largest power of 2. Basically, when we divide 290 by 2, we get 145, which has no more powers of 2. When we divide 24 by 8, we have 3, which again has no more powers of 2. When we divide 2 by 2, we have 1, which has no more powers of 2. So we're just dividing we're just dividing out all the powers of 2. So all the powers of 2 multiply to 32. So we have 5 total powers of 2 that have a product of 32. So that's why it's 2 times 8 times 2. Yeah, so then this problem, since it has to be greater than or equal to 37, let's just check the different possibilities. So if it's 37, does 37 work? So 37, let's just say we put 37 here. So remember the second condition that 2 of you are off by 1. So 2 of you are off by 1. So 37, is it off by 2 people? Is any 2 guesses off by 37 by 1? Yes, 36 and 38. What about this last condition? 8 is a prime number. Is 37 a prime number? Yes, again. So you see that 37 does indeed work. And we don't even have to check. We got a little bit lucky here. We don't even have to check any more possibilities. 37 just ends up to work, which is great. Now let's take a look at the next problem. After Euclid's high school last basketball game, it was determined that 1/4 of the team's points were scored by Alexa. So 1/4 Alexa. 2/7 by Brittany. And Chelsea scored 15 points. And none of the other 17 members scored more than 2 points. So what that means is that, let's just say the total team's points is P for points. So 1/4 of the team points was scored by Alexa, 2/7 by Brittany, plus 15 by Chelsea, plus some number between 0 and 14. We don't know what number we want to add here, but it's going to be some number between 0 and 14, because each of the other 17 members scored no more than 2 points. So at most, the other 17 members could have scored 14 points, and at minimum, 0 points. And this in total is just p points. So p equal to this quantity. So what we can do here is we can simplify this equation. We have that 7 over 28p plus 8 over 28p plus 15. So plus some number between 15 and 29. We don't know what number we want to add, but it's going to be some number equal to p. We can sum both sides. We get some number between 15 and 29 equal to p minus 7 over 28p minus 8 over 28p, which is 13 over 28p. So let's say p is 28, or if p is 28, then this quantity is going to be 13. Then 13 over 28p equal to 13. And is that possible? No, because we have that 13 over 28p has to be a number between 15 and 29. Okay, sorry, I should have mentioned this. P has to be multiple of 28, because if p is not a multiple of 28, then this quantity is not going to even be an integer. So p has to be multiple of 28. So let's just check the multiple possibilities of the multiples of 28. So we check p equal to 28. That doesn't work. If it's 56, then 13 over 28p is just 26, which is between 15 and 29. That's great. So we see that p equal to 56 does indeed work. So that means we have 56 points. Oops. Yeah, I keep forgetting that their image in the bottom of the screen. Okay, so as you can see here, that let me just quickly summarize the cases if you didn't see it. P equal to 28 doesn't work. P equal to 56 does work because you get 26, which is in this range, 15 to 29. So that means that 26 points are scored by Chelsea and the other 17 members. And that means that the other 17 members scored 26 minus 15 points equal to 11, because Chelsea scored 15 of those points. That means 11 is our answer to this problem. So if there are any questions, feel free to leave them in the chat. So now we're going to explore something called triangular numbers. Triangular numbers, as you can see here, they look like a triangle. They're called triangular numbers because if you put the numbers in a triangle, they look like a triangle. So here's what I mean by triangular numbers. So this first triangular number here is going to be 1, because we just have, imagine one dot. So the first triangular number is 1. If you have one dot, you're just going to be 1. The second triangular number, if we have one dot here and 2 dots at the second row, then we have a total of 3. So the second triangular number is 3. The third triangular number, well, we just had 1 at the top, 2 in the second row, and 3 in the bottom row. So the third triangular number is 6. And I think it's pretty clear by now that we always add another row to the bottom that's 1 more than the previous row. So we add 4 to the bottom of the third triangular number to get 10. And in general, the nth triangular number, so n triangular number, is just going to be 1 plus 2 plus 3 plus 4 all the way till n. And if you remember from previous class, we learned a formula that this is equal to n times n plus 1 divided by 2. Okay, so now we know that this is n times n plus 1 divided by 2. Let's actually explore a math counts problem that uses this concept. What fraction of the first 100 triangular numbers are evenly divisible by 7? Okay. So again, the nth triangular number is n times n plus 1 divided by 2. So we're asked to find, when will this be divisible by 7? So I'll give you a minute to try this out on your own. So the idea here is that in order for this to be a multiple of 7, we must have different factors of 7 in these numbers. Okay, so as I wrote out here, in order for this expression to be a multiple of 7, either n has to be a multiple of 7, or n plus 1 has to be a multiple of 7. So either n will be a multiple of 7, and if n plus 1 is a multiple of 7, that means n will have to be 1 less than a multiple of 7. Because if n is 1 less than a multiple of 7, when we add 1 to it, it becomes a multiple of 7. So as you can see here, the only time this will be a multiple of 7 is if n is a multiple of 7 or n plus 1 is a multiple of 7. Because there's no other way for this expression to have a factor of 7 in it. So now we just count how many numbers are multiples of 7 or 1 less than multiples of 7. So we just see numbers that are multiples of 7 are 7, 14, 21 till 98, or 7 times 14. So there's 14 numbers in this case. And in this next case over here, we have that there's going to be 6, 13, 20, etc. We just subtract 1 from these numbers till 97, which is again 14 numbers that are 1 less than a multiple of 7. So total, there are 28 numbers, less than 100, that will make this expression a multiple of 7. So our answer is just 28 divided by 100, which is 7 over 25. So that's a good trick for solving these types of multiple problems. And if you have time to, we might get to another one of these problems at the end. Okay, so now let's take a look at this next problem. In a tournament, there are 6 teams that play each other twice. A team earns 3 points for a win, 1 for a draw, and 0 for a loss. So 3 for a win, 1 for a draw, and 0 for a loss. After all the games have been played, it turns out that the top 3 teams earn the same total number of points. What is the greatest possible number of total points for each of the top 3 teams? So those of you who took the AMC 8 last year might recognize this problem. And it was actually considered one of the hardest problems this year on the AMC 8. So now let's explore how to solve it. So we have 6 teams that play each other twice. The top 3 teams, let's just call them A, B, and C. The bottom 3 teams, let's just call these bottom 3 teams D, E, or let me just write them here actually. D, E, and F. So these are the top 3 teams. A, B, and C are the top 3 teams. D, E, and F are the bottom 3 teams. So there are 3 kinds of games that can be played. So we can either have the top 3 teams play against each other. So these are the possible games that the top 3 teams can play each other. And the other possibility is that the bottom 3 teams can play against each other. So we can have something like this, maybe. So these are the possible games between the bottom 3 teams. So as you can see here, there are a total of 3 possible games between the bottom 3 teams. But we're given that top 3 teams, we're given that they each play each other twice. Oops. They play each other twice. So that means there are 3 possible games here. 3 times 2 equal to 6 games between the teams of the top 3 teams. We're going to just do 3 possible games times 2 because each game is played twice. And now let's look. We want to maximize the total points. In each game, we either have 2 teams have plus 3 for a win, and we either have 1 team get 3 points and 1 team gets 0 points, or we have both teams get 1 point. And if 1 team gets 3 points and 1 team gets 0 points, that means the total number of points given out is 3. But in the second case, if one team has 1 point and one team has another point, the total number of given points is only 2. So as you can see, clearly, more points are given out. More points are awarded when you have the first team get 3 and the second team gets 0. So the first team must have 3, 0, for a total of 3 points. So how can we maximize the number of points? We can clearly maximize the number of points if one team wins. Because if they tie, overall, less points are being given out. So these 6 games, we award a total of 18 points at most. And again, we want to maximize it, so we always choose the highest possibility. And same thing here. There are 3 times 2, 6 games, and 6 times 3 equal to 18. 18 possible points awarded at most. But now, there's also another type of game that can be played between the top 3 teams and between the bottom 3 teams. So these are the type of games that are different amongst them. So we can have maybe something like A versus A. We can have something like A versus D, or A versus E, or A versus F. Or maybe you could have something like B versus D, B versus E, B versus F. Or C versus D, C versus E, C versus F. So in this case, we have a total of 9 possible games. 9 possible games times 2, right? Because each game is played twice, so 18 games in this case. But in these 18 games, at most 3 points are awarded. Again, right? For 54 points. But when will the Was there anything unclear on this problem? Okay, I'll just continue. So at most 54 points are awarded. So when will it be the maximum case? When will we want to maximize the total number of points the top 3 teams will have? So how about we just give all 54 points to the top 3 teams in this case? Because the reason is we want to make sure that the top 3 teams have the most number of points. So how about in each game between the top 3 teams and the bottom 3 teams, we always just make sure one of the top 3 teams wins every single time. Because we want to maximize the total points the top 3 teams will get. So as you can see here, we have 54 points for the top 3 teams and 18 here. So at most, the top 3 teams can get 54 plus 18 equal to 72 points. And 72 points the top 3 teams can get divided by 3, right? Because each of the turns out the top 3 teams earn the same number of total points. So 72 divided by 3 equals 24 points at most per team. And this is a tricky problem, and then a really nice solution. So this is a really good instructive problem. Let's take a look at our next problem. A baseball league consists of 2 4-team divisions. Each team plays every other team n games. Each team plays every team in the other division m games, with n greater than 2m and m greater than 4. Each team plays a 76-game schedule. How many games does a team play within its own division? So this is a very similar problem to the last one. So let's explore. So we have A, B, C, D. And then we can also have something, we have 2 4-team divisions, A, B, C, D. Let's just say call them on one team, and E, F, G, H on the other division. And we're given that each team plays every other team in its division m games. So for A, for example, can play B m times. It will play C m times. And A will play D m times too. So A is playing each of the 3 teams in its own division m times. So for a total of 3m games. So 3m total games are played between A and B, C, and D, the teams in its own division. What about teams in the other division? Well then, A can play with E and every other team in its division n times. So it should be n, sorry. I just put m by accident. So this would all be n, so 3n. And then A will play with, this would be n, and N. And we'll play with other teams. Maybe M time we'll play with E. So we place each teams in games, and then each team in every other division M games. So M games amongst these 4 teams. So M, M, and M. So for a total of 3N plus 4M games, which equals to the total of 76 games that they play, each team plays. So how can we solve this equation? What we might notice is that M has to be greater than 4. So that means M has to be greater than or equal to 5. So M has to be at least 5. So if M is equal to 5, let me just do my case on the side here. If M is equal to 5, then N, 3N plus 20 will be equal to 76. But that means 3N will be equal to 56. But that's not allowed, since 56 is not a multiple of 3. So this case has no solutions. The next case is M equal to 6. M equal to 6. That's just going to be 3N plus 24 equal to 76, which means 3N equal to 52, which again has no solutions. And the final case is M equal to 7, which is 3N plus 28 equal to 76, which means 3N equal to 48, which means N is 16. Okay, so as you can see here, we do have a valued value of N. So N equals 16, N equal to 16. And this does indeed satisfy our condition of N greater than 2N, because 16 is greater than 2 times 7. But what if we continued on? If we continued on, we would also find that M equal to 10 is a solution. So if M equal to 10 is the solution, then that means that 3N plus 40 is 76, or 3N is 36, and that would mean N is 12. But you might think, okay, maybe the solution also works. But it actually does not work. The reason it doesn't work is that 12 is not greater than 2 times 10. So this solution doesn't work too. So our only solution is therefore M equal to 16, N equal to 16. So a team will play, in its own division, will play a total of 21 games. Sorry, we'll play a total of 48 games. 16 times 3 equal to 48 games. And it will play a total of 28 games with the other division. And as you can see, that does indeed satisfy our equation, so we're good here. Now let's take a look at our, so because we started a little bit late, we'll also just do one more problem, because we started a little bit late. So on June 1, a group of students standing in rows with 15 students in each row. On June 2, the same group is standing with all the students in one long row. And on June 3, it's just standing with one student in each row. And on June 4th, the same group is standing with 6 students in each row. This process continues through June 12th, with a different number of students in each row per day. However, on June 13th, they cannot find a new way of organizing the students. What's the smallest possible number of students in the group? So this is a really long and tricky wordedly problem. So let's see what it actually means. So basically what it means is that there's these different arrangements of a certain number of students. And they can make 12 of these such arrangements. But they can only make exactly 12 of these arrangements. Because on June 13th, the 13th day, they're not able to make an arrangement. So we can see here that, let's say the number of students is N. N will have to be a multiple of 15, because there are 15, on one day, there are 15 students in each row. And on another day, there are 6 students in each row. So that means N will have to be a multiple of 15 and 6, or N will have to be a multiple of the LCM of 15 and 6, which is 30. So N will have to be a multiple of 30. So if N has to be a multiple of 30, now what we can do is we can actually see that, okay, N will have to have 2 times 3 times 5, at least. And then we can multiply it by some other numbers. But the idea here is that we can make exactly 12 different arrangements. And what that means is that N must have 12 factors. And the reason this is true is that for each arrangement, let's just say you have an arrangement, for each arrangement, the width and length, the first dimension, second dimension, we can just take all the different factors of n to be the first dimension, and then the second dimension will just be the n divided by that factor that was used. So for example, let's just say we have 2 by n divided by 2. Because 2 is a factor of n. And then similarly, we can also have for each of these factors, we can get a different arrangement. So if we have the 3 is also a factor of n, we know that. So 3 can also, we can do something like n over 3. And maybe even 6. 6 over 10 over n over 6. For every factor of n, we have a different arrangement. Okay, so now that we have a different arrangement for each of these possibilities, we have a total of 12 factors. That means we have 12 factors of n. 12 factors. So, as you can see, in order to get 12 factors, since 12 is 2 times 2 times 3, our exponents must be 1, 1, and 2 by the factor trick. Remember, we add 1 to the exponents and multiply them to get the number of factors of a number. So our exponents of the factors must be 1, 1, and 2. So we can just do something like 2, 1, and 1, for example. Or we could also do maybe 2 times 3 squared times 5 to the 1. Or we could do 2 times 2 to the 1 times 3 to the 1 times 5 squared. These all have 12 factors. And remember, we must have a 2 times 3 times 5 because it has to be a multiple of 30. And it has to have 12 factors because on the day 13, we cannot find any arrangement. So it must have exactly 12 arrangements or 12 factors. And therefore, we can see here that 2 to 1 times 3 to 1 times 5 squared, this is just 60. This is just going to be 90. And this is actually the largest, which is 150. And clearly, this is the smallest, so 60 is our answer. Smallest students. The reason it's the smallest is because we have the largest exponent on the smallest factor. Okay, so that's going to be it for this class. Today we talked about number theory and how to apply it to a variety of problems, such as GCD LCM, money problems, and miscellaneous problems. So thanks for coming to this class. I hope you see everyone next class. Thank you. Next class we'll talk about geometry.